All right, let's jump right in. Today, we're going to talk about a single, mind-bending idea from 1905 that just completely changed how we see light itself. Seriously, it's a story about a stubborn mystery, a truly wild hypothesis, and one beautiful little equation that changed physics forever.
For centuries, pretty much everyone thought the debate was settled. Light, it's a wave, right? Spreading out through space just like ripples on a pond. Case closed. But then, as we turned into the 20th century, a weird little experiment involving light hitting a piece of metal started spitting out results that made absolutely no sense. The old theory wasn't just a little bit wrong, it was failing, big time.
So, on one hand, you have the old view. Light is this continuous, flowing wave of energy. But in 1905, a young patent clerk named Albert Einstein comes along and proposes something totally different. He says, what if light isn't a wave at all? What if it's actually a stream of tiny individual packets of energy? He called them quanta, but today we know them as photons.
Okay, so what was this big mystery that was giving everyone such a headache? Well, it was called the photoelectric effect. The basic idea is simple. You shine a light on a metal plate, and sometimes it can actually knock electrons right off the surface. Sounds easy enough, right? Nope. The way those electrons were behaving was just bizarre, and it completely flew in the face of everything the wave theory of light predicted.
So here was the real head-scratcher. Just think about waves at the beach for a second. A bigger, more intense wave is going to hit you with more force, right? That's what scientists thought about light. If you crank up the brightness, the intensity, well, the electrons that get knocked off should fly away with a lot more energy. But here's the thing. Experiments showed the brightness of the light had zero to do with the energy of the electrons. None. It was a complete and total contradiction.
And this is where Einstein comes in with his game-changing idea. He basically said, hey everyone, let's stop thinking about light as this continuous wave and start thinking about it like a hailstorm of tiny little bullets. These energy quanta, or photons, each carry a specific, fixed amount of energy, and that energy is determined entirely by its frequency, which is really just its color.
Einstein's idea was just so brilliant in its simplicity. He said, forget the wave, just think of it as a clean, one-on-one collision. One single photon comes in and smacks into one single electron, transferring all of its energy in that one instant. But, and this is key, there's a catch. See, the electron is kind of stuck to the metal, and to get out, it has to pay an exit fee. In physics, we call this the work function. If the photon doesn't have enough energy to cover that fee, well, that electron is going absolutely nowhere.
And this right here, this is the whole idea in one of the most famous equations in all of physics. Think of it like a simple money transaction. The input is the energy of that incoming photon, which is just h, Planck's constant, a fundamental number of the universe, times the light's frequency, v. The cost is that exit fee we just talked about, the work function. And the output? That's whatever energy is left over, which becomes the electron's speed, its kinetic energy. So, the electron's final energy equals the photon's starting energy minus the cost to get out. Simple as that.
But hang on a second. Look closely at that equation. It says K max. Why are we talking about the maximum kinetic energy? That little word maximum is actually a super important detail. What's that all about?
Well, that equation describes the best-case scenario, the perfect shot. Imagine a photon hits an electron that's sitting right on the surface of the metal. It escapes cleanly, no problem, with all that leftover energy, the maximum possible. But what happens if the photon dives a little deeper and hits an electron buried inside the metal? Now that electron has to fight its way out, bumping and crashing into other atoms along the way. By the time it finally emerges, it's lost some of that initial energy, so it comes out with less than the maximum.
The mark of a truly amazing theory isn't just that it explains something we already saw. It's that it makes brand new predictions. Predictions that you can actually go out into the lab and test. And Einstein's little equation, it made 4 very specific, very bold, and at the time, very weird predictions about how this all had to work.
Okay, prediction number 1. The energy of the escaping electron depends only on the light's color, its frequency. So, as this graph shows, if you crank up the frequency, going from red light towards blue light, the electron's maximum energy goes up in a perfect straight line. It's about the quality of the photon, not the quantity. A billion low-energy red photons can't do what a single high-energy blue photon can.
And prediction number 2 flows right from that exit fee idea. If a single photon doesn't have enough energy to pay that fee, the electron is stuck. Period. It doesn't matter if you shine a super bright light with billions and billions of these underfunded photons. If they can't pay the price individually, the door stays shut. There's a hard cutoff, a threshold frequency,
and if you're below it, nothing happens.
So this is what brightness actually does. It has nothing to do with giving any one electron more energy. Cranking up the intensity just means you're sending in more photons. More photons means more one-on-one collisions, which means more electrons get knocked out. So a bright light gives you a bigger flow of electrons, a bigger current, but the energy of each individual electron doesn't change one bit.
The old wave theory had this weird idea that if the light was really dim, an electron would have to sit there and just soak up energy over time, kind of like a solar panel slowly charging a battery, until it finally had enough to pop out. But Einstein's model, it's a collision. It's instant, like a cue ball hitting the 8-ball. And guess what? Experiments proved him exactly right. The very instant a photon hits, an electron is ejected. No waiting around.
Now you can imagine, an idea this revolutionary wasn't just accepted overnight. Oh no. For years, most of the physics community was really skeptical. It actually took an entire decade of incredibly careful work by one particularly brilliant and skeptical scientist to finally put the debate to rest.
And that brings us to this guy, Robert A. Millikan. Millikan was not a fan of this newfangled quantum business. He thought it was, and I quote, reckless. So he set out on a 10-year-long mission, conducting the most precise experiments imaginable, with one clear goal in mind: to prove Einstein's photoelectric equation was completely wrong.
So how on earth do you even test this stuff? It's not like you can put a tiny little speedometer on an electron. Millikan used a really clever trick. As the electrons come flying off the metal, he would apply an electric field pushing back against them, sort of like a headwind, and he'd crank it up just enough to stop the very fastest ones in their tracks. The voltage needed to do that is called the stopping potential, and it's something you can measure very accurately. And when you put that value back into Einstein's equation and shuffle the terms around, something magical happens. It turns into the simple high school equation for a straight line, y equals mx plus c.
And this is why that is so powerful. Einstein's theory made a concrete, testable prediction. It said, if you plot the stopping potential you measure on the y-axis against the frequency of the light on the x-axis, you must get a perfect straight line. No ifs, ands, or buts. And not just any straight line, the steepness of that line, its slope, had to be a very specific number. Planck's constant h divided by the charge of an electron e, two of the most fundamental constants in the entire universe.
And here it is, the stunning result. After a decade of painstaking work, trying his absolute best to find a flaw, Millikan's own data produced a perfect, undeniable straight line. It was exactly what Einstein had predicted. And when he calculated the slope from his data, it gave him a value for Planck's constant that was shockingly accurate. In one of the greatest twists in the history of science, the man who set out to destroy the theory ended up providing its ultimate proof. You just can't make this stuff up.
So let's just put it all together. On one side, you have Einstein's hypothesis, a pure thought experiment. Light comes in little packets, and their energy depends on their color. On the other side, you have Millikan's hard experimental data. His precise measurements confirmed that straight-line relationship and proved, beyond any reasonable doubt, that light really does behave like a particle.
So solving the photoelectric effect wasn't just about closing the book on one little puzzle. It actually threw open the door to a whole new reality, one that was much weirder than anyone could have possibly imagined. And this is the real beauty of physics when it's at its best. One simple, elegant equation that perfectly connects the world of light and radiation with the world of matter and electrons. It explains everything about this bizarre effect in one line. And this isn't just some abstract idea, it's the real-world principle behind the solar panels on your roof and the digital sensor in your phone's camera. But here's the final twist. In solving this one great paradox, physics created an even deeper one. This experiment proves without a doubt that light is a particle, and yet other experiments prove just as clearly that light is a wave. So, which is it? The profound and deeply strange answer from quantum mechanics is that it's somehow both. It chooses which face to show us depending on how we look at it. And that, well, that's a whole other mystery for another time.